Here they come. Oop, there's a nice push, people. Fantastic. Good evening, everybody. Welcome. Thanks for joining us tonight. Weathering the Storm, part 4 of 6 of this webinar series. Thanks for joining. I got 6:29 on my clock, and we'll get started in just a few minutes. Please hang tight in the meantime. All right, I've got 6:33 on my clock. John, thumbs up if you're ready, and I'll do some intros. And fantastic. All right, everybody, thank you very much for joining us tonight. Part 4 of 6, Weathering the Storm, our seminar series. For those who I have not yet met, I'm Doug Zemeckis, the Marine Extension Agent with Rutgers Cooperative Extension. Tonight's webinar and the 6-part series, being hosted by Rutgers Cooperative Extension, is a collaboration between 2 of our other long-term programs, Earth Day Everyday program and MEPS, our Marine Extension Program Seminar Series. Collaborating on this are my other colleagues, extension agents, Dr. Steve Urjo, Dr. Amy Rowe, Dr. Sal Mangiafico, and Michelle Bacchus. Pausing to reflect here, hard to believe, but the objective is, now 10 years since Superstorm Sandy, the anniversary coming up this weekend. Pausing to reflect and evaluate on how New Jersey has hopefully become more resilient in the decades since Hurricane Sandy to environmental impacts, particularly storms and extreme weather such as hurricanes and other types of weather events we experience here in New Jersey. So this is part 4. All recordings for the previous sessions, the first 2 are posted, the third one's in progress of being posted. But we started off with Dr. Dave Robinson from Rutgers University, who spoke about weather and climate. Dr. Tom Harrington from Monmouth University was up second, speaking about his work on coastal resiliency here in New Jersey. And last week, we had Tanya Rohrbach from New Jersey Future, speaking about adapting to climate change. Some navigational aids for tonight's webinar. We're expecting about 1 hour or maybe a little bit more total, including presentation and Q&A. We'll have 2 periods for Q&A, about halfway between and at the end. If you have Q&A, please put them in the Q&A feature. I'll be going through those, and we'll get through as many as we can within the time constraints halfway through and at the end. We are recording tonight, and the recording will be posted along with others on our Rutgers Cooperative Extension YouTube page and the Earth Day Everyday program page. Next slide, please, John. So at the end of tonight's program, during the last Q&A period, Dr. Steve Urjo will initiate a poll. We appreciate your feedback on that poll as a part of a research study that we do for program evaluation for this and other programs. Your feedback will be very helpful to help improve this and other educational programs that we offer through Rutgers Cooperative Extension. What this form is showing is the consent for you to participate in that study. Well, we'll use your feedback to evaluate this program and consider it in future extension programs. We are recording tonight, so if you need to take a look back at this consent form, you can check out the recording to follow up afterwards. Additionally, you'll be asked for your consent as the first question of the evaluation form at the end. Next slide, please, John. And also, we here at Rutgers Cooperative Extension, we're an equal opportunity program provider and employer working to make our outreach and education programs through Extension accessible and available to as many people as possible throughout the state of New Jersey. We're ticking up over 70 people now, about 400 people registered for tonight's program. So hopefully that's a good indicator of us making useful programs available to folks throughout New Jersey on important issues such as tonight, looking at resiliency since Superstorm Sandy. John, next slide. If you bring up your title slide, I'll give you a more formal introduction. So it's a pleasure to have this evening introduce Dr. Jonathan Miller. He's a research associate professor in the Department of Civil, Environmental, and Ocean Engineering at Stevens Institute of Technology. That's where he did his undergraduate with the bachelor's in civil engineering. And then he got a master's and PhD in coastal engineering at the University of Florida. His work and his lab at Stevens Institute focuses on the impact of coastal hazards on developed shorelines using field data collection, numerical modeling, so different approaches to better understand the resilience of built and natural systems. So a great expert here to share with us some of his perspectives and observations of progress that's been made with living shorelines here in New Jersey over the past decade and some perspectives for the future. John, thanks very much for joining us tonight. I'll turn it over to you.
Thanks, I appreciate that. The only thing I would add to that great introduction is that I am a lifelong New Jersey resident. So it's one of the greatest thrills that I have is that that I get to apply my knowledge to the beaches and the marshes and the areas that I grew up in. You know, as much as great as it was to learn in Florida and to have spent some time in Australia and really a lot of great beaches, there's nothing like being able to try to utilize everything that you've learned to basically help your home state and help them manage situations like what we saw with Hurricane Sandy. So we're going to start, I think, by just reviewing a little bit about Superstorm Sandy, and then we'll get into a little bit about the two topics that I'm planning to discuss today: living shorelines and beach nourishment. I don't want to take it for granted that everybody knows everything about those two topics. So we'll review that a little bit and then kind of move on to some of the work that's been done in the state since Superstorm Sandy, and hopefully how it's contributing, show a little bit about how it's contributing to resilience in the decades since Superstorm Sandy. So I'm sure if those of you who may have watched all of the seminars thus far, and I'm sure Dave Robinson did a much better job and much more detail than I could ever possibly do. But Superstorm Sandy was a very unique storm for this area, but it was not one of a kind though. You know, we've had many storms in the past. You know, the reason actually that I got into doing what I do is when I was in high school, we had the perfect storm, which was a nor'easter that happened in the 1990s. And I distinctly remember watching video footage from that storm, waves pounding on seawalls, massive beach erosion, a lot of the same things that we saw during Superstorm Sandy. Fortunately, not quite the same level of damage. Still certainly a lot of damage, but not to the same extent. But that was really what sparked my interest in studying storms and coastal erosion and resilience. So these storms do happen. They do tend to happen along our coast, and they're not necessarily unique events. So the big thing about Hurricane Sandy or Superstorm Sandy, as it became known, is that it was a huge storm. So comparatively speaking, Superstorm Sandy was a Category 0 storm, so it wasn't even a hurricane when it made landfall. It had just kind of lost a little bit of wind, a little bit of strength before it made landfall near Atlantic City. Yet the damage we saw was extreme, and it had to do with the sheer size of the storm. Just as an example, I'm sure obviously Ian is in the news right now, all the damage down in Florida. Compare that to Category 4 storm, or Hurricane Michael that happened in Florida several years ago. That's a Category 5 storm. And here in New Jersey, we saw damage that was on scale or on par with that type of a storm, even though Sandy wasn't even a Category 1 storm. So Sandy set a number of records. Some of it's kind of listed here. It's the lowest central pressure ever observed north of Cape Hatteras, North Carolina. The central pressure is a measure of storm strength. So the lower that central pressure, the more extreme the storm. The graphic I really like here, it just kind of shows an example, and we use this a lot in the time leading up to Sandy's landfall, and then afterwards, just to put it into perspective, because Katrina at the time was kind of the storm of record, the thing that everybody remembered. So Katrina here is shown with a radius of 230 miles, and Sandy was nearly twice the size of Hurricane Katrina. Not quite as intense, but certainly much, much larger. So what does the size of the storm have to do with things? Well, the size of the storm has to do with how widespread or extensive the storm surge was, but also the waves. Waves are one of the sort of maybe underappreciated parts of a hurricane that contributes greatly to their destructive power. So just some statistics here on this slide about the size of the waves during Hurricane Sandy. The one that I find like the most amazing as somebody who studies this is that during Sandy, waves that were in excess of 12 feet, so 12 feet, think about that, and basically 1 story tall, a little bit taller, that covered an estimated area of 1.4 million square miles, or a size of the ocean roughly half the size of the contiguous United States. So think about like how big the United States is. Out in the ocean, there were 12-foot waves covering in a span, at least 12 foot tall, covering a span that large. Again, just shows the sheer size. Particularly or more locally, the storm generated waves that were 32.5 feet at the entrance to New York Harbor. So now think about a 32-foot tall wave that is extremely destructive. And so we saw these types of wave heights up and down the coast, from Cape May all the way up to Sandy Hook. In addition to those waves, there were massive storm surges, right, that are associated with Hurricane Sandy. Here's just an example. The plot on the left is an example of a modeling system that we run at Stevens. The colors basically indicate the amount of storm surge. If you're taking a look, if you are looking closely, you'll see numbers like 4, 2.7, 0.2. Those are meters, unfortunately, on the plot on the left. So I apologize for that. But up near Sandy Hook, you're talking about 12 feet or so of surge during Hurricane Sandy. The 2 plots on the right are the actual tide gauge records from from Cape May. I'm sorry, on the bottom, and then Sandy Hook on the top. Cape May, the storm was much less significant in the southern part of the state, basically south of where the storm made landfall. So you'll see water levels of around 9 feet. Up north near Sandy Hook, you see water levels that approached 12 feet before the gauge actually went out of service, right? So the water level was so high that it wrecked the gauge there at Sandy Hook. So big spatial gradient in terms of the water levels that were experienced along the coast from Cape May up to Sandy Hook. Storm surge sometimes is not the best kind of way to describe things because it's hard to understand, perhaps. Much a little bit easier maybe is inundation level. So this is basically water level above ground. So this is if you're standing on the ground, how high is the water? And so what you see here on the left is, or the graphic on the left is from the Corps of Engineers, and it kind of shows depth of water above ground. So you can see that again, down south Jersey, Toms River, 4.5 feet above ground. Once you get up towards Sandy Hook, you've got 9 feet above ground. So think about that, standing there, 9 feet of water. I don't know if anybody in the audience is 7 feet tall or 6 feet tall, right? Nobody's 9 feet tall. I know that, right? So just to give a sense of, the enormity of, or how much water was pushed on land during Sandy. And then the graphic on the right just kind of shows the top 10 high water events in Manhattan. So you had, really the idea there is that the takeaway is if you compare the top 10 events and then you see Hurricane Sandy at the end, that Sandy was significantly larger than anything that had been experienced before, right? So, several feet more than what had been experienced in previous storms. There are lessons to take away from this as we kind of design moving forward, because, one of the takeaways before the storm is that you just design to whatever the previous high storm was, right? So don't even worry about all the details, all the math that can be involved and all that kind of stuff. Just, we made it through Irene, so we'll design to Irene's water level. We made it through the perfect storm in 1991. So it's designed to that level. But this kind of just shows that, it's not a perfect, it's certainly far from a perfect way to design, because if you had done that, Sandy would have outpaced your design by quite a lot. So just something to kind of keep in mind. So this is kind of now getting to the point of why we're here. It's talk about natural and nature-based features or living shorelines and beach nourishment and how they relate to resilience and damage. So and I'll just say NNBF is a term that is used interchangeably with living shorelines. It stands for natural and nature-based features. That's a term that the Corps of Engineers uses, and actually the international community uses to refer to living shorelines projects. So if you see NNBF, it just means living shorelines. What's intended to be shown by the graphics here, kind of two things. The plot with all the circles, the graphic with all the circles here, basically bright yellow means stuff that was damaged during Sandy. The more muted yellow is our structures that had minimal damage. What I found interesting in kind of reviewing data after Sandy was that there's this little sort of natural wetland kind of area here. And this is from Seaside Park, I think. And in the vicinity of that, and it's not just entirely due to the presence of that feature, but I did think it kind of stood out that the structures in that vicinity tended to not have as much damage as structures on either side where there's bulkheads. In the picture on the more zoomed out version of New Jersey with the reds and the oranges, that's from a study that the Nature Conservancy did after Sandy, looking at the amount of damage prevented by marshes and wetlands. So the ability of marshes and wetlands to soak up or suck up some of the energy associated with the storm surge and the waves. And so they found significant reduction in damage. They found $625 million in direct flood damage avoided due to the presence of marshes and wetlands. And so living shorelines are approaches that we use to try to generally protect those marshes and wetlands. So it's a combination of the structures themselves, providing some benefit to the communities, but it's the structures protecting the marshes, which are providing an additional benefit to the community. So it's the combination of the structures and the natural habitat that is providing benefit to communities. The two quotes at the top, the first two bullets, actually just speak to the fact that after Hurricane Sandy, there was a call to consider a wide range of protective options to help us increase our resilience to future storms. Considering a wide range of options, basically the full suite of options, basically calling on us to do more than we have ever done before, and to begin to incorporate things like living shorelines in our toolkit when it comes to increasing or improving resilience from future storms. Similarly, we could look at beaches. So, and I personally consider beaches living shorelines. I consider beaches, the beach nourishment, the first sort of living shoreline project that we typically have ever done. Beaches were also shown to reduce damages. And so here, the photographs are illustrating two photographs here. The upper photograph is from Ortley Beach, and the lower photograph is from Seaside Park, I believe. So Ortley Beach, Seaside Park, roughly a couple miles apart, 2 miles apart, something like that, maybe where these photographs were taken. The big picture in the middle is the beach as it looked prior to Hurricane Sandy. So you see both cases, nice wide beach. The big difference between the top picture and the bottom picture, Ortley Beach, very tall, skinny, narrow dunes, and the bottom picture in Seaside Park, an expansive dune, much wider dune. And then the pictures on the right illustrate the damages after Hurricane Sandy, right? So on the right-hand side in the top, you see the boardwalk in Ortley Beach completely destroyed, homes lifted off their foundations, complete destruction, utter destruction. Whereas in Seaside Park, you'll notice that a big portion of the dune is missing, but you'll also see that the houses, for the most part, look intact. And that was really kind of the benefit of having that beach and dune system, is that it protected those houses from the storm surge and the waves. And this just kind of highlights it in a different way, but same kind of, the dots over here are kind of the same thing. So the muted yellow dots are the no damage, and then the reds and the oranges are sort of complete destruction, right? Like completely damaged homes. The Ortley Beach is up there in that area where the red and the orange dots are, homes completely obliterated. Seaside Park is down there at the bottom where those muted yellow dots are that indicate that the home survived. And then plotted there on the left is data from Stockton's New Jersey Beach Profile Network, just comparing what the beaches look like in Ortley Beach, Seaside Park, and Midway Beach prior to Hurricane Sandy impacting the coast. And really, what's highlighted here is that the yellow, which is Ortley Beach, again the most damaged. You see how much smaller the beach is, how much narrower the beach is, and how much smaller the dunes are than Seaside Park and Ortley Beach. I mean, than Seaside Park and Midway Beach. Again, just kind of highlighting the fact that the communities with the larger beaches and bigger dunes tended to survive better during Sandy. So, so really, again, now that we've kind of illustrated the importance or talked a little bit about Superstorm Sandy and the importance of Sandy to resilience, wanted to talk a little bit about what are living shorelines and beach nourishment. I'm pretty certain that most people are maybe more familiar with beach nourishment than living shorelines. The graphic here kind of is a cartoon that is put out by NOAA, and there's a variety of these that are out there. So the idea with the living shoreline is that it utilizes either utilizes natural materials or tries to construct something that mimics a natural feature, which provides both protection to some sort of an eroding shoreline generally, but also tends to provide habitat for whatever community is, whatever natural community is living in the area. So in a little bit more detail, the definition that you see here is quoted is from New Jersey's coastal zone management regulations. So this is how they define a living shoreline. It's a shoreline management practice that addresses the loss of vegetated shorelines, beaches, and habitat in the littoral zone by providing the protection, restoration, or enhancement of these habitats. So it's something that aids in the assistance of the survival of these habitats. And it's kind of scattered here, and we'll kind of go through this in a little bit more detail, but just different examples of what a living shoreline might look like. And what you want you to take away is that it's quite diverse, right? Like none of these pictures look exactly the same. So there are mixtures of materials being used, some rock, some concrete, some vegetation, some coconut fiber rolls, core logs. So really there's a whole bunch of different materials that can be utilized in living shorelines. So just kind of walking through living shorelines, we can start with bioengineering, and this is really where, when I give presentations sometimes and I talk about living shorelines, sometimes I'll call it a newer science. And then it's pointed out to me that it's not really new because we've been doing bioengineering for many, many years, stream bank restoration and other things. It's really, I guess, the application in more open water environments and I guess the description that we use, the words that we use to describe it that are new, not so much the techniques. But bioengineering, you see a variety of examples here. Basically very heavily reliant on plantings, either live plantings or in some cases non-living plantings. Just the idea of kind of trying to utilize, in many cases, root systems to sort of stabilize loose soil. The roots tend to bind the soil a little bit, provide a little bit more resistance to erosion than sort of unvegetated shorelines. If you kind of go to like the next step up, and I think you can go to like plantings, which is just type of a bioengineering. So you see examples here up on the right hand side. This is an example from Sea Grant in North Carolina, where just some very simple planting restoration of vegetation along the shoreline, done in a very linear, regular, unnatural planting scheme, turns into, if it takes hold, can turn into something like what you see below, where you get this more expansive vegetation, which then holds in the soil or the sediments. You can kind of go a step beyond that and talk about natural structures. Basically, as we kind of step through these, we're starting to think about, like, as the energy increases, you tend to see a little bit more structure in addition to the natural elements to try to, a lot of times just to try to give the natural elements a head start. So a lot of times we use things like coconut fiber rolls or core logs. It's kind of what you see in this upper picture here. at the base of plantings to provide temporary protection, let the roots stabilize for the plantings. And then the idea is that these natural materials, these coconut fiber rolls or core logs, which are biodegradable, eventually disappear, leaving a sort of completely natural vegetated shoreline. But if the coconut fiber rolls weren't there to begin with, the vegetation wouldn't have time to take hold. So you kind of can add some of these more natural structures. You can begin to use combinations of what we call traditional structures and natural systems. So you see here now on the right-hand side are examples of a rock sill, basically stones designed and piled in a certain way to provide energy break or energy dissipation. So you can kind of see in that upper picture, calm water behind and a little bit wavy water on the outside of the structure. Planting behind it, either manually or naturally letting vegetation recruit in that area and sediment fall out behind the structure. Ultimately, hopefully restoring a marsh system there behind the sill. On the left-hand side on the bottom is a example from Berkeley Island. This is a New Jersey project now. This is Berkeley Island in Ocean County. And it's a stone sill with actually a wooden bulkhead utilized as a spine for the project. So it's kind of another level of to handle higher energy and to reduce the potential for sinking of the rocks due to poor subsurface sediments. We can use living reef structures. So living reef structures are very similar to stone sills. The difference here is that you're either trying to restore the reef naturally or use artificial substrate. So a lot of times we'll see different types of concrete products used as a substrate, depending on the environment, either seeded or not seeded, to encourage the settlement of any natural elements in the area, such as oysters or mussels. The advantage, if you can utilize something like a living reef, is that there's a potential for the structure to kind of keep pace with sea level rise. So you get that natural recruitment that can build or strengthen the element, the hard element over time. And this is really kind of taking back to what used to exist naturally in New Jersey. Used to have a lot of oyster reefs, in particular, that just over time have disappeared. So this is really trying to bring back something which historically had provided protection to a lot of our marsh shorelines. And then we can go even one step further, and these are like, wow, these are really living shorelines. And this is kind of like, okay, we have really developed shorelines. What do we do along these really developed shorelines? So what you see here are a variety of different approaches. The one in the big one there in the lower left, that's but that's Fort Myers, not Fort Myers, it's Fort Pierce in Florida. And so the idea here is that the funky shaped stuff down here provides protection to the marina and the community back here. Why is this a living shoreline? It's a living shoreline because these islands are specifically designed for habitat purposes for different types of birds, as well as other animals as well. Upper right, this beautiful picture with Manhattan in the background. That's an example of a artificial tide pool, which is created out of a ecologically enhanced concrete designed to encourage stuff to grow. So you can actually see some green inside of that tide pool, and it's basically provides the sort of the start of the food web, right? So a very simple element, things like algae can grow in these environments, and then that becomes food for the more complex organisms, crabs and fish ultimately and whatnot. And then the bottom right is an example of a park in Australia, actually, using different types of elements to create some pockets for fish to kind of swim in between. And so that's what that's an example of, those are examples of living shorelines. So that's really kind of what I wanted to cover in terms of what is a living shoreline. Yeah, I did want to talk a little bit about beach nourishment. Again, I think most people probably are more familiar with at least the basics of beach nourishment because it's such a popular thing in New Jersey, controversial thing in some cases in New Jersey. So at its very simplest element, and this figure kind of illustrates the beach nourishment, right? So you have some sort of an eroded profile, beach profile down here at the bottom. beach nourishment is the addition of sediment, typically to bolster that beach profile. And when we talk about beach nourishment, we typically think of ocean coast. So we think of, the big projects on the Atlantic Ocean. But we can also do beach nourishments and have some examples of nourishments in environments like Delaware Bay, where the nourishment is not necessarily intended to protect communities. Even it's intended to restore habitat for things like horseshoe crabs. Horseshoe crabs are very important to red knots, and red knots are critically endangered species. Horseshoe crabs are also important for horseshoe crab eggs are used for medical trials. So there's as crazy as horseshoe crabs look, they serve a very vital purpose, and restoring habitat for them is important. So the idea of beach nourishment, it seems very simple. Dump a lot of sand on the beach. One thing I do want to kind of highlight, hopefully, or point out, is that it's not as simple as just dumping sand on the beach. Beach fills are designed, they are engineered projects. The idea is to restore an eroded shoreline by adding sediment, but we do that in a very specific way. Typically, it's done through sand brought to the beach by either in small cases or at smaller projects through trucking sand to a beach and then dumping it and then molding the beach. In other cases, it's done by dredge. So most of the Atlantic Ocean nourishments are done by dredge. But the idea about how we place sediment is we really place it in a way that's the cheapest for us to be able to place it. And then we allow the natural processes, the wind and the waves, to kind of shape that beach to a more natural configuration. That's why after a beach nourishment project, a lot of times the beaches are extra steep. Sometimes they have cliffs immediately after nourishment if a storm occurs. But the idea is that over time, those beaches, those waves and those winds are going to move the sediment from where it's placed to areas underwater, where if we were to try to place the sediment underwater, really expensive and really hard to do. So the graphic here on the right just kind of illustrates a typical beach fill. So the one on the top, A, kind of just shows that that dotted line. The dotted line, I don't know if you guys can see the cursor, hopefully, but that dotted line kind of illustrates sort of the extent, like how much sand we actually place. That sand is actually partitioned into 3 different kind of quantities. The first is what's called the equilibration fill. That's the fill that is intended to actually fill the offshore portion of the beach profile where we can't place it. That's that darker orange sediment. And that's intended within the first year, really, to move offshore and kind of fill the deeper portions of the beach profile. The advanced fill is the extra sediment that is added to a beach fill to accommodate for, to provide protection for the length of time between the designed renourishment interval, right? So that's the extra sediment, which is providing protection. And then the design fill is really what's important. The design fill is what all the calculations about the benefits of a beach nourishment project are based on. So the idea is that you put out this sediment, the equilibration happens pretty quickly. And then over a period of several years, that advanced fill generally also starts to erode away. And then once you get back to that design, that's when you add more sediment. So the design fill is really the minimum beach that you should have at any specific time. And all the benefits are based on that. So if you have more sediment than the design, then you actually have more benefit than what the benefit to cost ratios are calculated on. So it's just kind of one of those things that's definitely not appreciated, because I know a lot of times it seems as though the sediment disappears as soon as it's placed. But at least a portion of that, the equilibration part, is supposed to happen almost instantaneously. And here's just an example of what beach fill might look like. Just some photographs that we took with our drone, I think at Long Branch. First picture on the left, you see a barge here offshore. Ultimately, the barges come in and the sediment gets pumped out on shore, where it gets moved around by earth moving equipment. And then on the right-hand side here, you see some staging of equipment typically seen in a beach nourishment project. So you see some pipes and whatnot. And the picture on the right is actually after beach nourishment. So you see a kind of temporary dune kind of pushed up after the beach nourishment project here in Long Branch. This is actually, if we're going to stop halfway, this is actually probably this is a good spot for me, because the next two parts are really looking at, okay, so what do living shorelines look like since Sandy, and then what do beach nourishments look like since Sandy? So it'd be a great time to stop if there are any questions.
Yeah, great. Really strong start there, John. Appreciate it. We have a couple good questions already, and they tend to trickle in once we pause. So appreciate you remembering. So we have this opportunity to ask you a few questions at this point. First one I'll throw at you is Steve is wondering, is there a best time of year to do beach nourishment?
That's a good question. So there are pretty strict restrictions in terms of when they're allowed to pump because of different nesting seasons, different habitat fish considerations. So they're very much restricted to the winter season. It's interesting. What it tends to happen, and we've been comparing two projects in Long Branch, one that completed in February, and then one that completed actually earlier in the fall, and they evolved a lot differently. The one that was completed in late February actually stayed pretty steep for many years, not for many years, for many months through the summer, because we just simply didn't have enough storms to kind of shape the beach. That natural process has never happened. Whereas the one that was completed in the early fall, there were a lot of winter storms that kind of more naturally sloped it out, so that there are restrictions, and then there have been, I think, if the intent is to have it equilibrate more rapidly and restore a more natural shape prior to the next season, I would say that finishing it up midwinter at the latest just provides the opportunity for more winter storms to kind of reshape the sediment and help that equilibration happen faster.
Great, thanks, John. Somewhat related there. Anonymous attendees wondering, how do you measure whether or not beach fill ends up where you hope it will go? Further out, underwater, as a question?
So I'm really glad. That was like one of the last things that I added to my presentation is I was thinking about different ways to kind of go with this. And in the second half of the presentation, we will talk a little bit about how we measure where the sediment ends up. But we do survey it and try to keep track of it as best we can. I have some examples of that.
Right on. Another question is, what is your opinion of using feeder beaches or sand engine or motor methodology?
So I think it's an interesting concept. They did try a feeder beach in Long Branch in 2008. We were able to monitor that project, and it seemed to be pretty successful. There are trade-offs. The feeder beach basically puts all the sand in one place. It's cheaper to construct generally. And then it just uses the natural processes to spread it out along the beach. Advantages of that are potentially that it covers up, like I know from fishing interests, surfing interests, et cetera, it covers up fewer structures immediately, therefore leaves them exposed for fishing and for surfing. So that disrupts those types of activities less initially. It does concentrate all of the protective benefit in one area, at least initially. So until it spreads out, you have one part of the coast which is extremely well protected. So if a storm happens, they're fine. But then the neighboring areas where it hasn't spread to yet, it may take some time for them to receive the full protection. What we saw in Long Branch is that those areas did receive the full protection, and it took roughly about less than a year, maybe like 10 months or so, for that sediment to kind of spread out. So I think it can be effective. I think it's something that we should think about more and do more. And this year they actually did a project down on Harvey Cedars where they actually, instead of nourishing the shore face, they nourished the nearshore area and basically built a really big sandbar offshore, and kind of same idea, same concept, let that sediment move out. So when you put all the sand on the beach, you kind of let it move offshore. And when you put it offshore, you're kind of letting it move onshore, right? So it's kind of two different things. And I've seen some initial monitoring results of that. And it seems like most of the sediment did remain in the system. But then that's a whole nother public relations issue when you pump sand from underwater into some other place underwater, because you don't see it immediately, right? So it's not as obvious in terms of what the protective benefits are.
Yeah. Interesting. Somewhat related, perhaps. Brooks has a question. Brigantine North End is scheduled for 3 projects with which you might be familiar: 270-foot, 75-foot seawall extension, 5 micro jetties beach fill replacement. Would you be able to explain the benefit of like what they're calling micro jetties, 5 of them, and how they can help hold beach replenishment? Do you know how tall something like that might be?
So I'm not familiar with the project, but from the description I can, the purpose of jetties or groins, and like we tend to call them groins if they're adjacent to an inlet, we call them jetties. I know I grew up in New Jersey. Every stone structure is a jetty. But the purpose of those really is to slow the longshore sediment transport. So that's the sand that moves along north and south, basically along the coastline. That's why after certain storms, you'll see sand built up on one side and eroded on the other generally. Historically, we did a bad job of designing these types of things, which is why there are some locations where it's really bad. Sediment's built up on one side all the time and it's really eroded on the other. Now we have a much better handle on how to design them. So that's what we call micro structures. Really, the intent is to not, we say the old way was really to block all of the sediment, and the new way is to sort of regulate or control sediment. So in a sense, it's supposed to serve sort of like a valve that, you can restrict the flow of sediment, but not completely stop it, right? So it provides a sort of a backbone and a basic template that we're hoping that the beach kind of stays in. So it's trying to help restrict the losses of sediment from the beach fill project, keeps it from spreading out too quickly.
Thanks, John. My own add question to that is the longshore transport to the north of about LBI, and then south of there?
So it varies from year to year. So a convenient delineation we use is Manasquan Inlet. And we say north of Manasquan Inlet, it goes north, south of Manasquan Inlet, it goes south. It has to do with the way that Long Island kind of shelters the northern part of the coast from bigger waves during nor'easters. So the nor'easters tend to drive the sediment to the south, predominantly in the southern part of the state. And in the northern part of the state, those waves are blocked. So it's the southerly swell, which is more dominant and kind of pushes the sediment to the north. But that can vary anywhere from, Seaside Heights, Ortley Beach, maybe that far south all the way to like Manasquan Inlet.
Mm-hmm. Good. I'm glad I remember something from my science and shoreline management class with Carl Nordstrom about 15 years ago. Cool. Carl asks, or I guess he's talking about the shellfish or the plants used, jumping to living shorelines now. Are there any agricultural applications from those activities related to living shorelines?
Okay, so agricultural applications. So this is an interesting, and I think I'm interpreting the question correctly. So it's interesting, living shorelines that utilize shellfish in particular have had a sort of tortured relationship or tortured existence in New Jersey because of the threat of poaching, illegal poaching or harvesting of shellfish, and the threat that might pose to the shellfish industry. So there's been a little bit of back and forth about we should be able to restore oysters, but what if somebody eats a bad shellfish or something? So there's been a bit of that relationship. Actually, I have a PhD student now who's really interested in kind of looking at existing aquaculture farms and how they may be benefiting in terms of attenuating waves on shorelines. And so she's really interested in kind of comparing that to because aquaculture tends to be more expansive, right? Covers more of a bottom area, but is not as tall necessarily, doesn't stick out of the water as much or at all in some cases. Whereas all the structures we built are peaky, they're very narrow and very tall. But there's benefits to sort of smaller, flatter, wider structures. So she's interested in kind of looking at the existing farms, aquaculture farms, and how they benefit. They may provide a benefit similar to living shoreline. So hopefully I'll have a better answer for that question in another year or two.
No, that's a helpful response. I'll just add, I know there's a lot of local shellfish farmers who produce the shellfish, spat on shell or cultureless oysters that go on. So there are some agricultural products, including from that area. Many people with us tonight are involved with those types of efforts with commercial growers or volunteer organizations. I'll do about 2 more while we're on this break and then let you get into the second half here. But Christine's wondering, are there any beach replenishment projects or examples from other countries, such as the Netherlands she commented on, that are useful models for similar conditions here in New Jersey?
So yeah, I think for sure. I think so. It's funny, after we had the opportunity to have several visitors from the Netherlands come over and work with us at Stevens after Sandy, and they were kind of commenting about the way that we do beach nourishment projects, and we were explaining why we do things a certain way and why we place sediment on the beach instead of underwater. We talked about the public relations issues. We talked about issues in terms of considering the interests of surfing groups and fishing interests. And they were very surprised to hear that we cared, because their response was, over there, they basically have carte blanche to do what they want to do because it's scientifically the best thing to do. And flood protection is taken that kind of, I guess, seriously there. So they were taken aback by the fact that we actually had to consider all of these different competing interests and competing factors. So we can learn, I think, from other places, but at the same time, just have to understand that, culturally, that there are things that they can do that we just are not set up to be able to do. So we're progressively trying things like the feeder beach concept. I think that's a great example. I think the Harvey Cedars project is a great example. I think by trying those types of projects, we kind of see and we can learn. And if we can document, the benefits of that type of a project, then it certainly helps in terms of changing the public perception, perhaps, and potentially the way that we do things here in the U.S.
Great. Thank you, John. Throw two more at you, although I said two that time, but I will cut it off at two more. Related to what you just commented on there, Nick asks, are there any plans to study the effects of beach nourishment on the habitats of beachside or in the surf zone marine life? Commented that replenishment has destroyed some of the unique outer bar cuts and hampered fishing for surf anglers.
Yeah, so I mean, we for the most part, Stevens is an engineering school, so we mostly study on the physical side of things, but we do work with other groups that have and do some of those studies on habitats. There was actually one of the graphics, the graphic I actually took that had the beach profile and the different segments of sediment, like the 3 different volumes. That comes from a white paper that the American Shore and Beach Preservation Association put out. It's a really good white paper, and I'll add the link when I actually make the slides available later. But it provides a good understanding of kind of the way that beach nourishments function. They did a similar paper or follow-up paper that looked at habitat impacts, which was actually done by a group of ecologists within the organization. So people much more well-equipped to kind of really comment on how it influences habitat. But yeah, I mean, it's one of those, my understanding of it is that, there's sort of temporary and there's long-term impacts, right? And, certainly, you have a storm like Hurricane Sandy, and that causes sort of a natural dramatic impact. And we obviously don't want to artificially introduce a Hurricane Sandy every time we do a beach nourishment project. But that's just to say that to an extent, there is an ability of the environment to recover because there are natural disruptions which have occurred over time. But we need to definitely be cognizant of what we're doing and study it to have a better understanding of what's happening.
Thanks, John. One more, building off Ann's question. Can you clarify the roles of like BOEM, the Bureau of Ocean Energy Management, Army Corps, and DEP in some of these beach nourishment activities along the Atlantic coast?
Sure.
If it's possible to streamline a response.
So streamline a response. Okay. The streamline response is BOEM generally does a lot of work with helping to identify borrow sources of sediment that are potentially useful for beach nourishment projects. The Corps of Engineers is responsible. Corps of Engineers has studied the majority of the New Jersey coastline and has contributed to the nourishment of a majority of the Atlantic coast of New Jersey. The federal government has a system whereby it's a cost share system in terms of these projects. So federal government pays 65% and the state pays 35%, or the local sponsor pays 35%. Within New Jersey, the state DEP basically absorbs 75% of the 35% of the local share, and passes on 25% to the communities that are involved. So ultimately, it works out for a local community. They pay basically 9 cents on the dollar is the number that's quoted. So for every dollar's worth of beach nourishment, the community pays 9 cents. The state government pays 65 minus that 9%, the 24%, and then the federal government pays the 65% share. So there's a cost sharing agreement. In terms of the actual work, the Corps of Engineers generally contracts for the work with the local the dredging contractors who do the construction. DEP and Corps are both involved in kind of making sure that they're done appropriately.
Excellent. Thank you for that response. Helpful for me and others. And I know you've been teaching all day. You're teaching part of your day job today and tonight. So while you still have energy, please let's jump into the second half. Looking forward to it, John.
Sure. Right. All right, so now is the fun part. We get to talk about living shoreline progress since Sandy. We'll go through some projects, some things that have happened. There are a couple of slides that have words, pretty word heavy. When I get to those, I'll probably move pretty quickly through them. Again, my intent is to make these slides available, so you can always go back and read through if you want, but I don't want to harp on it, especially because it is getting later. So one of the things that helps us in New Jersey immediately after Hurricane Sandy, and this was work that was in place prior to Hurricane Sandy, the state DEP was looking for ways to implement more living shorelines projects. And I had been involved maybe 3 years prior to Hurricane Sandy on how we can write regulations to allow us to do more living shorelines projects. So once Sandy happened, that process kind of accelerated, and the state passed what's called the Living Shoreline General Permit. Just makes it much easier to get funding to do or to get permits to do living shorelines projects. There's a number of these bullets talk about the number of the kind of aspects of it. One of the really cool things about our state permit is it allows us to fill out to the 1977 tidelands line if the purpose is for habitat restoration. So in a lot of other states, you're basically limited to working above the mean high water line, which means that anything that's been lost, you can't restore it really. It's almost impossible to restore. So in New Jersey, we are allowed to go back and kind of reset the clock. So if we're losing marsh edges and things like that, we can restore marsh out to that 1977 line, which is a very unique, helpful aspect in getting these types of projects pushed forward. DEP did also at the same time work with us at Stevens to develop a set of engineering guidelines with the intent of basically providing guidance to a community, which particularly an engineering community that had not been familiar with living shorelines up until that point. So we were building coastal structures like breakwaters and revetments and seawalls and familiar with those types of things, but not how do you incorporate natural elements. So we worked with them to develop this guidance in 2013. We actually just submitted a revised set of guidance in 2020, taking all the lessons that we've learned since Hurricane Sandy, rolling them into a kind of updated best state of the practice kind of document that just describes how to do living shorelines projects. So just to talk about some of the interesting projects that we've been involved in, or that have been built in New Jersey, just kind of illustrate, I guess, the diversity of the different things that we've done in New Jersey. Berkeley Island was one of the first projects we were involved in. Berkeley Island's a county park in Ocean County, just south of Toms River. And the kind of 3 time-lapse photographs here kind of march through time. What you see in the upper photograph is a shoreline, parking lot for the county park. See the shoreline, you see trees along the shoreline, so you see vegetation, it's kind of healthy. The middle picture is right after Hurricane Sandy. You can see sediment overwashed into the parking lot. We were actually working with them prior to Sandy. The parking lot was being threatened by erosion. Rather than just putting up a bulkhead, they wanted to work with us to try to implement a living shoreline project there. And then what you see at the bottom is the restored project after Hurricane Sandy, where you can see offshore, there's a series of breakwaters or sills with gaps, allows for access for animals to kind of get in and out between the structures, water to circulate behind the structures. And then vegetation, again, revegetated along the shoreline edge there. Up close, so this is kind of more what it looks like. You can get a better sense of kind of scale, I guess. So this is looking from This is looking from this area over here, the Google Earth logo, basically, back towards the project itself. So you see the cove with the beach, which was preserved, and then the series of stone sill structures, gaps in between. The gaps, again, allow for that water to circulate in behind the structures and allow for access for animals to get in and out, fish to swim behind, etc. The structures. This one was kind of unique. We actually designed it with, this one actually has a bulkhead, wooden bulkhead spine. You can kind of see it peeking through the rocks here. Originally, we didn't design it that way. It was supposed to be just a stone structure. One of the issues that we see in some of these environments where these projects are going to be built is subsurface sediments just being of really poor quality, such that any sort of heavy structural material will tend to sink. So in this particular case, that bulkhead spine was added to ensure that the wave attenuation would persist even if the stones were to settle a little bit. And you can actually even get a sense of the wave attenuation. If you look behind the structure here, it's basically flat glass. And then on the outside, you can see some small wave activity, right? But that's the intent of these structures, not so much in these conditions, but in a little bit more energetic conditions to kind of protect that edge of the edge of the shoreline from erosion. This is an interesting one. This is Gandy's Beach. Gandy's Beach is the inset up here, kind of shows its location. It's on Delaware Bay. Gandy's Beach. This project was interesting because it was constructed as a sort of a trial and error or experimental project with U.S. Fish and Wildlife to look at could something like an oyster castle, and that's what this structure is here. It's an oyster castle. Let me close that. This structure here is an oyster castle. It's basically look like concrete. They look like cinder blocks, like Lego blocks made out of concrete, special type of concrete designed to encourage oysters to settle on them. So clearly oysters are having a good time settling on these structures. The idea is that eventually they become encased by the oysters so that the concrete substructure is not even exposed, or not even, you don't even know it's there anymore. The picture at the bottom here just kind of shows there was a series of these structures kind of laid out along this section of marsh, eroding marsh. It was experimental because this type of an approach had never been used in such a high energy environment. So the tidal range here is 6.5 feet. It's exposed basically out to Delaware Bay. So you get significant wave activity, 2-foot waves, maybe even higher during the right conditions. So the structures are effective in some ways and less effective in others. This was kind of cool because it was a project which was constructed and actually studied. So a lot of monitoring going on here. People studying the fish, people studying the oysters, people studying the marsh vegetation. We're studying the physics of the wave transformation. Actually, you can see these little poles here are all just elements of different scientific studies going on. So this has been studied for 6 or 7 years now. And we're learning a lot about it so that we can apply it to other designs. This is Iowa Court. Iowa Court is in Little Egg Harbor Township. Again, the progression of photographs that you see here just kind of go through time. So this is like, and I try to leave the dates here on the bottom just so, you know, as we're kind of going through this, if I forget to mention it. So the photograph here is from 1995. You see there's a significant marsh kind of edge out here in front of these homes. Fast forward to 2019. You can see that basically the homes are directly exposed now. The marsh is kind of completely eroded from in front of this section here. The roadway, which is cul-de-sacs right here, was being undermined during major storms. So a living shoreline project was constructed to provide a sill, right, or again, to attenuate the wave energy. That's what you see in this picture here, that stone ribbon along the outside. And the consulting company did the same. It's the same one that did Berkeley Island. So there's a wooden bulkhead spine here. And then the idea is to kind of do restoration, marsh restoration in here through planting to restore that marsh that was existing there. We weren't involved in the design on this one, but it's just another kind of example. Picture here on the left just shows you what it looked like. This was prior to, it was 2013. So you can see that that cul-de-sac, you can see where the road was being undermined here at the edge. There's no marsh out in front. And this is kind of the restored project with that wave attenuation structure on the edge. You can probably kind of tell it from here, but this area has begun to revegetate. So you can see the vegetation kind of taking hold in here. So hopefully it doesn't look like this barren sand crescent for much longer. Forked River Beach, again, just a time lapse here from left to right, showing healthy beach kind of along the communities here in Forked River. The second picture kind of shows less healthy beach here. And then the third picture kind of shows basically a rock line shoreline. In this particular location, they're trying a new technique. And the reason that I included this was this is a brand new project. This is a American Littoral Society project where they're installing these HESCO baskets. That's what you see here on the lower left. Basically, they're wire baskets filled with combination of stone. They have like an interior section, which is made out of stone, and then an exterior section, which is made out of shell. Again, the idea is that the baskets are providing substrate for additional recruitment of natural shellfish in the area to attach to. And the baskets themselves are providing wave energy attenuation. So there's a series of these, and unfortunately, I don't have a plan view that kind of shows it, but there's a series of these basically all along this shoreline here, built to provide wave attenuation for that section of Forked River Beach. And then again, really the reason for including this is another project. This is at the Lighthouse Center, and I forget where this one is, but you can see it here. This is Barnegat Inlet, so just inside of Barnegat Inlet. And the reason that I included this was because this is just like what the hell is this? These are examples of different, I call them proprietary wave attenuating devices. These are actually called WADs, wave attenuating devices. But there's a whole series of these products. You saw the oyster castles on one of the previous slides. This is an example of a WAD. There are things called reef balls. They're like literally, if your mind can imagine it, there's probably something that looks like it. So there's a whole host of these different types of structures which are promoted by various companies that provide, basically intended to provide wave attenuation. And they all have some something special about them. I didn't want to say gimmick, but there's something about them that makes them different, unique, right? The holes that are kind of, you see here, these triangular holes, the idea is that it allows water to flow through. It allows fish and things to swim in between the structures. It's also intended to slow the water such that when the water reaches the inside, it drops out any sediment that might have in it. So the intent of these is really to kind of slow the wave energy, slow the current energy, and drop sediment on the inside of the structures and naturally build back the marsh, which has eroded behind it. A lot of these, this is again, sort of a small section of a project which has been installed to kind of see, hey, are these things working or not? Because you don't want to go wholesale, armor the entire coast with these things before you understand if they're working or not, right? So this is where we kind of get involved somewhat on the academic side, is we look at different projects like these and try to figure out what works. So I have a student that's monitoring the HESCO baskets, for example, because I want to understand how the HESCO baskets work. So we're trying to figure out which of these things work the best, what configuration they may work the best, how tall they need to be, how wide they need to be, things like that. Along the way, this is one of those very wordy slides. The list over here is just some of the things that have been developed to help in the design of Living Shorelines project. So there's a variety of resources out there. Everything that's blue is hyperlinked. So again, once the slides become available, they're point and clickable, just to kind of illustrate the types of resources that are available. A lot of the environmental groups in the state, Partnership for Delaware Estuary, the Nature Conservancy, some stuff from Rutgers, NIFWIF, or National Wildlife Federation. There's a lot out there. A lot of people have been doing work in New Jersey. So there's a lot of different tools that have been developed. This is our tool, so this is why it gets its special treatment, right? It's a Stevens tool. So this is the guidelines that we had mentioned before. I mentioned that we had updated our Living Shorelines guidelines. A couple things that are just important for future adaptive management. That's kind of a big buzzword. That's something that the international community is adopting a lot right now. The idea that if you want to design something, how is sea level rise, for example, going to impact a structure that you build? If you build it very close to the water line, what happens when sea level rises? Now it's underwater. Is it still going to be effective? So we don't want to overbuild today, specifically because we don't know what sea level is going to look like in the future. So the idea is to build in structures that have an ability to be adapted over time. So as we understand more about sea level rise, is the trajectory really high? Is it trajectory the moderate trajectory, or is it the low trajectory? Then we can adjust when we have more certainty about things like that. So adaptive management is a key. And then beneficial reuse is also something that has become more and more. And again, this is one of the things that I'm excited to work in New Jersey, because we are beginning to talk a lot more about beneficial reuse. For a while, sediment was discarded as a waste resource. So when we dredge areas, get rid of it as quickly and as fast and as far away as possible. Whereas now we're beginning to think about, okay, all the sediment that we have, where can we use it? Can we use it to rebuild the edges? Now that we have the Living Shorelines general permit, we can build back to the 1977 tidelands line. Can we better use that sediment on shorelines to restore eroding marsh shorelines? On the platforms of marshes, a lot of times the marshes are sinking. Can we add some of that material on the top through something called thin layer placement? So how do we do that? And so we're talking a lot more about that. New Jersey is being very progressive about trying to conserve that resource. So that's also added into our guidelines. And then the other thing that we did is we developed this sort of eco shoreline on developed coasts, which is really a sister document to our original Living Shorelines guidelines, just designed for what do you do when you have these really more urban, more developed shorelines. So ultimately, we looked at case studies and we looked at other guidance that's out there and kind of developed what we call a set of core design principles. So those design principles are things that we are encouraging New Jersey to look at when designing projects along shorelines that are developed, that are more dense. So there are things you can do like increasing surface roughness, so adding in these different elements, allowing light penetration. This is an example of the Seattle Seawall project. Fish tend to like light. Their behaviors change when it's dark all the time. So how do you do that in an urban environment? Tide pools, increasing water retention. Again, water retention generates the ability for simple organisms like algae to kind of develop, and then that can generate more complex organisms using alternative materials. This one's really cool. This is like a regular concrete down here on the left-hand side, and then a ecologically enhanced concrete on the right-hand side. So the intent is the combination of the change in the concrete matrix, design matrix, plus the little roughness elements here. Look at the difference in the growth on these two different elements. So small changes, small impacts in terms of costs can have big impacts in terms of the ecological impact of the project. And then just more urban, these are actually from the Harlem River Designing the Edge. Examples where they've kind of reduced slope by adding in terraces and introducing curvature by kind of stepping back the wall here, creating little niche habitats for small fish to kind of hang out and grow. Beach nourishment. Since Hurricane Sandy, in 2012, 50% of our Atlantic facing coast was part of a U.S. Army Corps coastal storm risk management project. In 2022, that'll be about 90% of the coast. So there's an 80% increase in the amount of our coast, which is part of one of these big federal beach nourishment projects. These projects are 50-year projects. They are designed to have renourishment over a period of time. And these are the projects that are constructed as a combination or a partnership between the federal government and the state. So lots of, again, pretty much the entire Atlantic facing coast for the most part. Just an example, and we were talking about this is the Yankees territory. So this is like, you could say New York district, I just say Yankees territory. So everything north of Manasquan Inlet, these are their projects. It's a sad face because unfortunately there's no conflict with the Yankee game tonight. So I'm not keeping anybody from that. So yeah, a bunch of projects that have, these are the projects that have been built since Sandy and the cost. So landing up to $734 million worth of project. Phillies territory, boo. I'm sad, but Phillies fans are happy. These are some of the projects that the Philadelphia district of the Corps of Engineers have done. $600 million worth of projects. So added up, you're in the billions of dollars of projects since Hurricane Sandy, various stages of completion. What do some of these look like? This is just an example. This is Manasquan Inlet to Barnegat Inlet project. This is basically, just some statistics on the project. the photograph kind of illustrates, again, what does a beach nourishment project look like? I like this one because it kind of shows that you have your pipeline with your sediment discharge. So sediment is being discharged here. Once the sediment's discharged, it's being moved around by various types of earth moving equipment, bulldozers and whatnot. It's shaping that dry beach to a specific specification, certain elevations and tolerances, certain widths and slopes. And then they just kind of progressively move along the beach, adding sections of pipe and kind of increasing the beach as they go. This is an example, and this is, I should have changed this here. I quickly did Manasquan Inlet to Barnegat Inlet. My brain went to Long Branch, but that's not Manasquan Inlet to Barnegat Inlet. But the pictures here are from Long Branch. So I'll point that out just to kind of show sort of the evolution of what beach nourishment looks like over time. Again, here on the left-hand side, this is the section of Long Branch, which is by Pier Village, I believe. And what we have here is on the left-hand side, 1995, so prior to any beach nourishment project. And this was the state of a lot of Monmouth County at this point. So like the entire northern part of the state, where you have seawalls, you have groins or jetties, right? And you can see this is that example where they build up on one side and a road on the other. So this zigzag sawtooth pattern up and down the state, very little beach at high tide, maybe a little bit of an exposed beach at low tide. Then here in 2008, we have a May 2008 photograph, which was immediately after a beach nourishment project. So you see that sediment has now filled out in each of these, what we call groin cells. Then you see 2009, again, the beach is still pretty strong, pretty healthy. 2012, this was immediately after Hurricane Sandy. So notice that there's very little beach left. The sediment has moved on. Again, part of the reason for the beach is to protect what's behind it. So although the beach itself is disappeared, a lot of the infrastructure behind it managed to survive. Here in 2014 is a renourishment. So you see the beach built back out again. And then all the way here on the right-hand side, which got cut off a little bit, that was the most recent photograph I could find. So I think it's 2019. One thing to point out, since it was brought up about the feeder beach, actually, if you look at the 2009 and the 2008, this particular section of beach was not directly nourished. This was part of the feeder beach. So the feeder beach was actually south. So it was down here off the page. That was where the feeder beach was constructed, and the sediment was moving north along the beach, which is why it's building up on the south side of the structures. So the sediment was kind of progressively moving to the north. It's interesting that in 2008, this was a couple months after the feeder beach was constructed. 2009 is like a full year afterwards. So you can see that the beach is actually wider in 2009 than it was in 2008, because all that sediment that was placed in that feeder beach is now working its way north along the shoreline. Whereas in 2014, this was a traditional sort of linear beach fill. So now they've covered all the structures, and it's a straight shot, right? So in terms of impacts to fishing that may be associated with these groins or jetties, or surfing that happens off the tips of those jetties or groins, here it's completely gone, at least temporarily, until they become reemerged. And here you still have some exposure of those structures. So this gets to the monitoring question. So how do we know what happens with the sediment? So we monitor. That's one of the things that we do. We have a system we call our duck system. Our mascot is the duck, Stevens Ducks. So hence it's called the Dynamic Underwater Coastal Kinematic Surveying System, or ducks. Consists of a drone, which we use to survey the subaerial beach. We have a walking backpack GPS unit, which we attach to students, send them out across the beach and out into the water. Yes, even in February and March and very cold weather. And then speaking of cold weather, offshore, we use a jet ski with a GPS and a sounder on it. This is one of our research engineers, Laura Kerr, looking very, very warm in her survival suit. But to be fair, she's cold all the time. So this was probably like September. So what do? Once we survey, we use the data we collect to create digital elevation models. So this is just an example from a recent survey we did in Long Branch. Left-hand side here is pre-fill. Middle one is post-fill. So if you compare the center section here, the center section is where most of the fill was placed. So you see the yellow kind of bump out here. That's just the indication that the elevation has been increased in this area. And then 1 year after the fill, what we can see is that the sediment has kind of moved along the shoreline. So this area is a little fatter than it was here. And this area is a little bit narrower because the sediment has kind of moved to the north and south as the beach fill has equilibrated. We can subtract the different elevation models to find out, or to be able to see more clearly where things have happened. So in this case, this first picture kind of shows where the beach nourishment took place. So all those yellows, that's where the sediment was directly placed. You look at the other figures, kind of going around clockwise here. This is sometime later. So now the sediment was originally placed here, but now it starts to spread to the north and to the south. So you can see that those yellow areas kind of spreading out to the north and to the south. And then the last one kind of shows the development of a big sandbar actually offshore, which is what we saw with the most recent nourishment, as a massive sandbar occur within 6 months of nourishment, and it's persisted actually all throughout this past summer. We can then do things like we can calculate the volume, so we can look at the volume of material placed. We can look at how the volume of material in different sections changes over time. So how much material stays within the placement area, how much material stays within the community of Long Branch, how much material can we find altogether. So we can start to look at kind of how that sediment is moving around, how much of it stays above land, how much goes underwater. So we can basically partition it and kind of pull it out and try to be as detailed as we want. We can also do things like looking at impacts on surfability. We had a master's student a few years ago in Long Branch specifically look at how the movement of sediment and the development of sandbars, how it occurred with this particular beach nourishment. This was a project which was constructed and finished in September. And we found that within 3 months, the sandbars had all come back because the winter storm conditions moved that sediment around, regenerated the sandbars. So this was an example of that idea of when do you finish a project? In this case, if you wanted to preserve the surfing or impact it for a small amount of time as possible, finish in September, October, those first winter storms move the sediment around and re-expose the sandbars and limit the impacts on surfing. We take this data and we can do modeling studies. This is probably a lot for this late in the presentation. But the gist of this is we use machine learning models to kind of try to predict or forecast or understand the impacts of storms. So what we did here is we took Hurricane Sandy and we said, okay, let's have Hurricane Sandy hit this particular section of, I think it's Stone Harbor. Let's run Hurricane Sandy and we'll take a look on the bottom here. This is like the beach as it was in 1986, 1987, 1988. So we have all this data that Stockton has collected about what the beaches look like at various points in time. And it's kind of a what if. So what if Sandy had hit in 1986? What if Sandy had hit in 1995? What if Sandy hit in 2012? What if it hit in 2013, right? So we're trying to figure out what kind of a difference the beach conditions make. And the gist of this is red is bad. Red means that the dunes were impacted severely. Blue is good. It means the impact to the dunes was minor. And yellow is kind of in between. It's moderate, right? So we can kind of look at something like this and we can say, oh, well, this is bad all the way up until 2003. Like you got major impacts all the way up until 2003. But after 2003, the major impacts disappear. Why did the major impacts disappear? So then we can dig into, well, what does 2003 look like? And we can find out that in 2003, there was a big beach fill project in this area. So what the modeling can show us is that the impact of this beach fill was to basically reduce the potential impact of the storm to the dunes, right? So instead of having major damage to the dunes during Hurricane Sandy, after the beach was just nourished, basically you're trending towards minor impacts or at worst moderate impacts. So you can see that the benefit of that beach nourishment was to reduce the impact on the dunes. And the dunes, of course, provide protection to what's behind it. So you can kind of use that almost as proxy too for whatever lies behind it. So we can kind of use these models to kind of try to understand what those, what the beach morphology, what kind of an impact it makes. And we can even begin to think about things like future scenarios. So what happens if we add sea level rise to Hurricane Sandy, right? So how is that going to change things? So we can do all of those things, and we have done those things. Last thing I wanted to just touch on, and there's no more graphs. I apologize, no more graphs, promise. It's just how do we combine living shorelines and beach nourishment? So I said I consider beach nourishment one of the original living shorelines projects. And so here's an example of a project that was just done at Money Island by DEP with FEMA money, and it really is a combination. It's a beach nourishment project. It includes some coastal structures, and it was designed really to create horseshoe crab spawning habitat. Money Island is down on Delaware Bay, just off of Nantuxet Creek. This is the shoreline restoration project. So on the left-hand side, 2016, here's Money Island, number of homes along here. This was also a part of a Blue Acres program. So a number of the homes were bought out after Hurricane Sandy and removed. After the homes were removed, so 2016, 2021 over here. So you notice there's no homes, fewer homes. Now the idea was to restore this area back to natural environment where horseshoe crab habitat was really important. The picture down on the bottom, 2020, kind of shows what the beach looked like. It was a pretty eroded state here, very narrow beach, not much space for horseshoe crab spawning. 2021, there was a beach nourishment project, beach fill as a part of the restoration. So you can see all the sediment that was kind of added to the shoreline here. Similar to Gandy's, we just talked about previously, pretty high energy environment. So in order to potentially increase the longevity of the beach fill, a series of offshore breakwaters were constructed. These happen to be just made out of rock, so they're not oyster castles like at Gandy's. But the idea of these structures is to reduce the wave energy, reduce the sediment transport, kind of preserve or lengthen the amount of time that sediment stays on the beach. And then hopefully this is what the result is. So you get habitat which is restored for the horseshoe crabs to spawn on. So again, example of kind of beach nourishment and living shorelines, tying them back together, hopefully kind of emphasizing the point that beach nourishment, although we tend to think of it oceanside, we might think of it as recreational or protecting communities. Here's a great example where beach nourishment is used and has been used in the past to really recreate habitat. And there's lots of opportunities to do that along marsh shorelines. And with that, that's the last slide that I have. So if there's any questions, I'm happy to take questions.
Excellent. Thank you very much, John. Really great presentation. It's wonderful to have a real expert on these important subjects such as you, type of people we try to bring in to bring science-based information out to the public and a variety of different stakeholders. And thank you, Steve, for throwing that poll in there. If folks could consent and provide your feedback on tonight, that'd be great, so we can continue to improve this and other extension programs. John, you said no more technical graphs. Well, I think what's impressive is an engineer just gave a talk for an hour and a half, and I don't think I saw any equations. So
I tried my best.
Save that for your undergraduate and graduate teaching, I guess.
Yep.
Cool. Mindful of your time, though, we'll get wrapped up here in a little bit, but I'll throw a couple at you, John. One attendee is curious to know, what are the controls for a living shoreline project? How do you interpret or understand the change you might observe?
That gets into the monitoring, and I think that's something that is, the state is very supportive of it. Yeah, one of the tough things is that the fundings oftentimes doesn't lend itself to continued monitoring, unfortunately. A lot of these projects are grant funded. There's a certain amount of money to design, build, and then really it requires somebody to step in and monitor afterwards. So we try to get involved in as many projects as we can. Some of the projects, there are monitoring requirements, which is good. I'd like to see more of that. And then, we try as best we can to identify control sites so that we have a good comparison, right? So not every site lends itself to that. Some of these sites are pretty unique, but wherever possible, we do try to implement a control site so that we can isolate the effect or the effect of the specific living shoreline project itself. But that's a really important part.
Thanks, John. Duly noted on the funding there. If not already, maybe some of the volunteer organizations throughout the state can help with the monitoring once grants are over. But cool there. So Christine's wondering, how can all the work in New Jersey along the coast continue to be done in a coordinated approach where we all inform each other and be more site specific in living shorelines work at the same time?
Yeah, that's a great question. Yeah, so that's one of the things that's pointed out in the Corps' new international guidelines for NNBF is that there's two parts of it, right? There's the monitoring, and then there's the passing along of that information, right? So the monitoring does no good if people don't know about it, right? So the coordination, the education, the outreach. So events like this they're actually pretty good to let people know about what's going on. And then, really we have to do a good job of kind of, and I think the state does do a pretty good job. There are a number of groups that I'm involved in that are the professionals that are kind of working in this space, trying to share with one another. I know the state's interested in trying to fund assessments of these projects with the idea of passing along the lessons learned. So hopefully some of that work does get done, and it'd be great to be involved with that and pass that along, because we need to know how to do things, what worked, what didn't, and how to do things better.
Thanks, John. Michelle was wondering, what is the lifespan of the ecologically enhanced concrete? How long does it hold up?
So really it lasts as long. Well, I guess there's two answers to that question. Bad ecologically enhanced concrete can be garbage. And some of the oyster castles that were originally formulated, they were not formulated, they were built for formulations for down south. So once ice happened in New Jersey, like the ice basically destroyed them, right? So that was a bad example, right? But that doesn't mean they all are like that. There are actually good examples of ecologically enhanced concrete. And I think there are applications where it's being used to encase pilings. And there's a couple big projects in New York City where they're trying to use this concrete with the idea that if oysters will attach, the shells will sort of calcify around the concrete and prevent actually chloride penetration into the concrete, which then gets into the rebar, which then causes rust, which then causes all sorts of issues. So there are examples where the ecological concrete, if in the right environment and there is natural recruitment, can actually be stronger than the original concrete and actually extend the life of the concrete. But absent that, really a well-formulated ecologically enhanced concrete can last just as long as any other. It's basically just putting in different types of admixtures. So it's no different than dealing with quick drying concrete or low water concrete. Same idea.
Cool. Excellent. Great response. Thank you, John. With that, actually, we really got through all the questions. Really impressive, the body of work that you and your collaborators have done that you were able to cover through the state. As noted at the beginning, that your lab does with numerical modeling, advanced AI and approaches, and also getting your hands dirty out there in the field for monitoring. So thank you for taking the time and sharing your knowledge tonight, John. Thank you to all the participants, co-hosts, and organizers, Steve, Amy, Sal, Michelle. The recording will be posted within a few days, we anticipate, on the Earth Day Everyday webinar series page, our Rutgers Extension YouTube page. Everybody who's registered will get an email to the link to the recording, and John's going to update some of his slides, and we'll get those out to you. The next two seminars, as a part of this Weathering the Storm series, November 14th, we have Chris Miller from the U.S. Department of Ag talking about flooding in agriculture. And then Jessica Conway on November 21st from NOAA's Marine Debris Program, talking about emergency response of marine debris, the plan that was developed specifically for New Jersey. So thank you again, everybody. Hope you enjoyed the presentation. Be well, and we'll see you hopefully on November 14th for the next one.